think it's like 6 slides, okay? But one of my things, oh yeah, before I get into chemistry, I finally want to show you this. Watch this. See if it comes up. It should. We should even have sound. This is that video I kept talking about. If you drop 2 objects here on Earth, the one that's got the aerodynamics going for it are gonna hit the ground first. But if you drop them in the absence of air, like you can do on the moon, then actually you end up with the objects accelerating at the same rate, which is 9.8 meters per second for every second they fall. They accelerate at the same rate and they hit the ground at the same rate. So this is finally that famous video. I think to chemistry. It's like it's going to have kind of a strange sort of dimensions to it, but I think we'll be okay. So one of the things about chemistry, I was thinking, what do I want you guys to pick up about chemistry? A few things. Some of the things is stuff that you already know. So I'm going to be building on what you already think you know. You probably do know it about chemistry. Chemistry gets a bad rap for being hard. I really don't think it's all that hard. The other thing about chemistry is I just want to draw you in, and maybe someday down the road you'll take a chemistry class. Okay? All of these disciplines. Take a physics class, take a meteorology class, take an astronomy class. Okay, so one of the things you probably already know is this concept of an atom. But aside from that, actually, anytime they talk about matter, they're talking about basically atoms. Okay, and they're talking about atoms that actually have a certain mass and they occupy a certain space. So the word atom is actually kind of the basic unit of matter. So matter is anything that has mass and occupies space. And here's all some things about an atom. Okay? So the concept of an atom is not that new. But what we're going to see here in a minute on a slide is what we know about an atom, kind of about something called electrons in an atom and protons in an atom. I mean, that kind of is new. So the word atom actually means to remain intact. So one of the things when we talk about an atom, this basic unit of matter that has mass and occupies space, an atom is what we say you cannot break it down any further. It's intact. So here I kind of brought, if you're kind of into, I can't remember, it's etymology, the source of words, or entomology. One's with insects and one is the other. Okay, so you can kind of see the origin of the word atom. So later on we're going to talk about how atoms join together to make compounds, and so you probably, I'm familiar with this idea that when you drink water, you're drinking actually 2 hydrogens and an oxygen, H2O. Okay, so those 3 atoms join together to make a molecule. So this is a figure, I believe, from your textbook that kind of, what we say, classifies matter. So matter is made up of atoms, and all matter has mass and occupies space. But we can kind of use this logic tree to what matter is. It's kind of like you ask yourself questions. You'll either go left or right based upon the answer to your questions. So right off the bat, matter can either be what we call a pure substance, okay, or matter can be a mixture. And they kind of make sense. So if it's a mixture, you think of stuff kind of mixed together. And literally, if you have a chunk of matter that's a mixture, you have just kind of tossed a couple of pure substances together. And you're what we say physically combining, like a tossed salad. Okay? A good example of a mixture is like a pizza. Okay? It's a mixture because you have the whole pepperoni, the cheese, the tomato, okay? So there's different types of mixtures. The pizza is what we call a heterogeneous mixture. Okay, it's non-uniform. Something that would be a homogeneous mixture, a good example is if you're making Kool-Aid. Okay, you'd start with water, which is pure, and you go to sugar, which is also pure. What makes water pure and sugar pure is it has the same repeating unit. The same repeating unit is H2O. The same repeating unit of sugar is C6O6H12, I think, something like that, glucose, sugar. Okay? What makes Kool-Aid a mixture is that you mix them together. What makes it a homogeneous mixture is if you're lucky, okay, when you're making your Kool-Aid, you make sure you don't have any sludge at the bottom. It's all homogeneously mixed together. So homogeneous means the same throughout. Well, if it's matter, it's made of atoms and has mass and occupies space, and it's not a mixture, then it must be a pure substance. And if it's a pure substance, okay, you have two options there. You can, and I kind of talk about putting on these glasses where you can see atoms. I don't think they exist yet, but maybe one of these days. So you put on glasses and you see the atoms, and if all the atoms are the same, you have an element there, okay? It's purely the same atom. If you put on the glasses and you see a repeating unit, like an H2O molecule, that's a compound. Okay, so we'll be talking more about each one of those, but that's kind of the logic tree of what matter is. So atoms, okay, you may kind of have this, actually I brought a BB today to kind of put atoms in perspective. Are atoms spherical? Probably. So one of the things I want you to get out of chemistry is what makes up an atom. And even though physicists actually, have you heard of like the particle accelerators, like the Large Hadron Colliders? The other few years ago, the Higgs boson, the God particle, was in the news. And basically what they do is they have these, physicists have these accelerators that they take like the size of a city, okay? They take a circle the size of a city, and that's the track for the particle. And then they take two particles, and I think they probably make them go around the track a few times, getting them faster. That's the particle accelerating. And then they ram the particles into each other. And they make little pieces of particles. We're not worried about the little pieces of particles. We're worried about these three, what we call subatomic particles. So in order to kind of understand an atom, you need to know at least these three particles. There are the electrons. The electrons are kind of buzzing outside the hard center, okay? Electrons actually, when it comes time for atoms to kind of, what could say, shake hands, when it comes time for a water molecule to, okay, of course you guys would probably tell me, you know, water is H2O, and actually the oxygen atom is in the center, like it kind of feels like, and then the hydrogens are on either side. When it comes time for the this chemical bond to form between an oxygen and the hydrogen, or this chemical to form between the oxygen and the other hydrogen, it's the electrons that kind of make that work. Those green things up there are chemical bonds, okay? These are chemical bonds, chem bonds. They are kind of like magnets. They're like, dude, it's like if you have oppositely charged magnets. Okay, yep. Chemical bonds. So electrons are negatively charged, which you may already know. They generally, what we say, bring no mass to the atom. The other subatomic particle to know is the proton. And the proton is positively charged. So the symbol is a P with a little plus for the positively charged. The location for the protons actually is are in the nuclei of atoms, the center, the hard center of an atom. I kind of think of the electrons are basically kind of buzzing outside in what we call an electron cloud, okay? In the center, not buzzing, well, kind of moving a little bit, is the nucleus that has the protons in it. Protons are really important subatomic particle in an atom because the number of protons, if you could put on glasses, not only see the atom, but if you could see the protons in the center of the atom, you would know what element it is. I just think that is so cool. Okay, in here and in this part on unit on chemistry, we'll be looking at the periodic table a little bit. So we have one on the board on the wall that I'll be referring to. So the periodic table, of course, each box you might recognize is a different element. Okay, and each box with an element has some good information. One good information is that it has the number of protons in the nucleus of each atom. And it's the whole number. I talk about the whole number. So can you see Ne? That's the element. What its element is that? Ne is 10. 10. Very good. And what's the name of the element? It makes signs light up. Neon, yep, it is neon. And 10 means it's got 10 protons in its nucleus. Okay, so if you skip ahead, the symbol K, what element is that? Do you guys remember? Potassium. K is potassium. Special K, I think bananas have a lot of potassium, you know. Yeah, so potassium K, you can see the red number 19. So it has 19 protons in its nucleus. That's pretty cool. So they're positively charged in the center of an atom. They say which element it is. That's pretty cool. They weigh about 1 AMU. You know, you figure atoms are really, really light, so we really can't even use grams to weigh an atom. Instead of that, what we do to weigh an atom is introduce a new weight, and that, or mass, I guess I should say correctly, and that mass is the AMU. So down here I have atomic mass unit, AMU. You're going to hear me, you're going to have to kind of make that translation because I learned it as AMU. The symbol for AMU is the letter U, atomic mass unit. So in terms of these three pieces of an atom I'm talking about, the proton is about 1 AMU. Okay? All right. Before I move on, and I think I might come back to it in my notes, but in case I don't. So the number of protons is the number of, the number of protons is what says what element an atom it is. Actually, we call the number of protons the atomic number, so I'm going to underline that in case you didn't already. The atomic number, okay, that's a player. Like if you're talking to people about elements or whatever, they'll say, well, what's the atomic number? You tell me atomic number, I'll tell you what element it is, okay? It's the number of protons in the nucleus of an atom. That's the atomic number. All right. So, last but not least, we have the neutrons. The neutrons are like Switzerland. They help basically all the protons in the nucleus to get along. Okay, so neutrons are like, they're neutral, they don't have any charge. And we go back to kind of to the magnets. You know how, like, if you have the magnets with the same pole, they will repulse each other? Okay, that's the same thing if you get a lot of charges, like protons, positively charged particles. Pick on potassium, okay, 19 protons in its nucleus. Those 19 protons would not want to be in close proximity to each other, okay? And so it's the neutrons that kind of help make that happen. Now, the number of neutrons in the nucleus of an atom, we're going to see that actually that kind of varies, okay? It's not set in stone. All right, so what else about neutrons? Well, they're located in the nucleus, helping the protons to coexist. They also weigh about 1 AMU, and they don't have a charge. Free. So atom-wise, this is kind of what we have going on. We have a nucleus with the protons and the neutrons, and we have electrons in a cloud outside. So this is why I brought a BB here. So in this figure, the kind of dark center is the nucleus, and you don't see the individual particles, but there's protons and neutrons in the nucleus. And kind of the lighter color is the electron cloud. So what this says is if you imagine a balloon that stands 10 stories high, okay, so 10 stories high, and you go up to about the 5th story, and you take a BB, and you hold it. So relatively speaking, what you now have is that is the size of a nucleus to scale. So 5 stories up, 5 stories wide, 5 stories down, 5 stories on all sides. That's about the where the electron cloud ends for the electrons drawn to scale. So atoms are small, okay, but the point is that nuclei are very, 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 very small, and most of an atom is just empty space, electron cloud. Most of atoms are empty space. So I've heard it described that kind of the reason that we can stand on the floor, okay, the atoms in my feet, okay, the reason the atoms in my feet don't go through the atoms in the floor is actually because the electrons in my electron cloud in my feet won't go through the electrons in the electron cloud of the floor. It's mostly empty space. So, kind of neat. So, model of the atom through time. So actually clear up here at the Schrodinger model in 1926, you can kind of see maybe the little fuzz, that's where the electron cloud, so the green one down here, okay, in the center of Schrodinger's model is a nucleus, okay? But that wasn't always what we knew. Back in, starting in 1803, Dalton came up with his, what we call atomic theory. And he just kind of piggybacked on the Democritus and the folks that kind of came up with the concept of an atom. He finally formally presented a paper on the theory of what an atom is. Okay, an atom is basically the smallest particle of matter. You can't destroy it. And then Thomson came up with, you can actually just, if you look at the yellow orb there, you can see what Thomson made. He made the discovery that actually within a given atom, there are positively and negatively charged particles working there. Okay, they didn't really know the idea of a nucleus yet. Okay, so that was 1904. And then you can kind of see the two purples. The dark purple would be finally the nucleus in Rutherford's model, and kind of the light purple is the electron cloud. Okay, that's the one, if I'm thinking of it right, and it's in your textbook, what Rutherford did. But basically, he sent a beam of energy at a very thin gold plate, a plate of atoms, as thin as he could get it. And what he saw was that most of the energy passed right through the film, okay, because it was finding holes in the electron cloud of the gold atoms. Every once in a while, the energy would come back because it hit the nucleus. Okay, I just think that is so cool. Then in 1913, the difference between the purple and the blue model is that the blue model actually, you can see there's something going on with the electrons. So the blue model now has electrons that, and when we come back on Monday, we'll be talking more about electrons. But electrons are not made equally. One of the things I didn't mention yet, and it will come up, should come up, is this idea of if you have an atom, let's pick on potassium. Okay, if you have potassium, which is atomic number 19, okay, so symbol for potassium is K, and it has 19 protons. Let's go ahead and make that the nucleus of the potassium atom. Okay, if it's neutral, each one of those positively charged protons, 19 positively charged protons, if it's neutral, need to have an electron in the cloud outside. Okay, so if it's neutral, actually we have 19 electrons out here to make a potassium atom. It's funny when I write something atom, to me that almost looks like cadmium, but it's potassium atoms. Okay. So that's a neutral potassium atom. And what Bohr came up with is important, and Schrodinger built on that, but he said those 19 electrons, they're awesome. They have individual identities, but they exist actually in what we call different energy levels. Can you see we have kind of an inner orb? This is supposed to be an electron here, and this is an electron. Okay, so we kind of have an inner electrons and we have outer electrons. And what Bohr and everybody after him said is recognize that those 19 electrons around a potassium atom, they organize. We're going to have to talk about that organization. So Schrodinger, then, like I said, kind of built on that. You know, in science, I love science because people just kind of pass the baton. And you never, like, reinvent the wheel, per se. You're always kind of skipping and jumping on what others have left you to know about. So Schrodinger came up with this idea. Can you kind of see that almost makes me itch? That the black dots in that green orb actually is where the electrons are. You really don't know where, for instance, those 19 electrons are around a neutral potassium atom. You kind of know a general region where they are, but you don't know exactly where they are. And so that's kind of the difference between the Bohr and the Schrodinger model. All right. So that's how far I wanted to get. And you already saw on the next slide, you know, I'm not going to put it up there because you fill in the blank. We're going to pick up we'll take one more look at this slide and then go on to the next slide on Monday. The next slide's going to talk about electrons and the whole board, different energy levels for electrons. All right.